Let's go. There's a version of the universe most people carry in their heads. Galaxies scattered through space like islands, distant, glittering, mostly separated by emptiness. Darkness between them, nothing between them. That version is wrong. The space between galaxies is not a vacuum waiting to be crossed. It is an environment. It has structure, it has a temperature, it has fields, forces, particles, and phenomena that science is only just beginning to map. And some of what lives out there has been staring back at us for billions of years without anyone fully understanding what it is. These are 12 of those things. And by the time we reach number 1, the word empty won't mean the same thing it did when you started watching. Number 12, Lyman alpha blobs. In 2000, a team of astronomers pointed the Keck Observatory in Hawaii at a patch of sky about 11 billion light years away and found something they couldn't explain: a massive cloud of hydrogen gas, glowing, radiating light at a very specific wavelength, 121.6 nanometers, the Lyman alpha emission line. And the thing was enormous. Larger than most of the galaxies they'd ever cataloged. This wasn't a galaxy. It had no spiral structure, no obvious stellar nurseries, no coherent shape. It was just a vast, shapeless mass of gas sitting in the intergalactic void, pouring out energy equivalent to hundreds of billions of suns. The problem was nobody could find what was powering it. Normally when a gas cloud glows, something is ionizing it, a quasar nearby, a cluster of young, hot stars, some ultraviolet source pumping energy in. The rule is simple: you need a fire to light the gas. The team searched exhaustively for that fire inside these blobs and in several confirmed cases found nothing adequate to explain the output. The largest of these objects span over 400,000 light years. That's several times the diameter of the Milky Way. We've cataloged dozens of them across the deep universe. Theories have accumulated for 2 decades. Some researchers argue hidden quasars buried inside dust clouds are the source. Others point to unusually intense star formation happening deep in the blob itself. A more unusual proposal suggests cold gas falling inward along cosmic filaments releases gravitational energy directly as light. No star required, no central engine, just gas collapsing under its own weight and glowing as it falls. Each explanation fits some blobs, none of them fits all of them. These things have been sitting out in the deep universe for most of cosmic history, radiating with the luminosity of entire galaxies, and we still cannot agree on what is making them shine. For structures that large and that bright, that is a remarkable thing to have to admit. Number 11, the cosmic web. In the 1980s and 1990s, as astronomers built the first large-scale three-dimensional maps of the universe, they expected to find galaxies distributed roughly evenly across space. Clustered in places, yes, but without any overwhelming large-scale order. What the data revealed instead was something that looked less like physics and more like biology, a vast web. Filaments stretching across hundreds of millions of light years, connecting clusters of galaxies at the nodes with enormous empty voids in the spaces between. The universe at its largest scale looks like a neural network, like the branching structure of a fungus, like a sponge. Soviet cosmologist Yakov Zeldovich had theoretically predicted something like this as early as 1970. Seeing it in actual data was a different experience. Here is the detail that spent decades hiding in plain sight. Cosmological models of the Big Bang predict a specific quantity of ordinary matter, all the protons and neutrons and atoms in the universe. For years, when scientists added up all the matter they could actually observe, stars, galaxies, gas clouds, everything visible, the total fell far short. Roughly half of all ordinary matter in the universe was simply unaccounted for. Gone. Missing. In 2020, independent research teams finally confirmed where it was. The missing matter had been hiding in the filaments themselves as an extremely diffuse, extremely hot plasma called the warm-hot intergalactic medium. So thin it had evaded detection for decades, so pervasive it contains half of everything. The skeleton of the universe was assembled before the first star ever formed, built from dark matter and early gravitational collapse into a structure that then determined where everything else would go. Every galaxy you've ever seen or heard of formed because it happened to lie along one of those threads. And the web itself is not static. Galaxies are still moving along it, still being drawn toward the intersections, still being shaped by the architecture that was laid down before the universe was 1 billion years old. Number 10. Intergalactic magnetic fields. In 2010, a paper published in the journal Science made a claim that astrophysicists found genuinely difficult to process. Using data from NASA's Fermi Gamma Ray Space Telescope, the authors reported detecting magnetic fields threading through the cosmic voids between galaxy clusters. Not near galaxies, not inside galaxy clusters, in the deepest, most isolated regions of intergalactic space, places where the matter density drops to roughly 1 atom per cubic meter. A magnetic field requires moving charged particles to generate and sustain it. In a region with essentially no particles, no current, no matter, a sustained organized magnetic field should not exist. By every conventional, physical expectation, it shouldn't be there. It is there. These fields are extraordinarily weak, measured in femtotesla, a unit so small it's a quadrillion times weaker than a common refrigerator magnet, but they extend across millions of light years. And crucially, their orientation shows a degree of large-scale coherence that can't easily be explained by simple diffusion over cosmic time. Two competing explanations have been seriously advanced. The first is that these are primordial fields generated in the very first moments after the Big Bang, possibly during a phase transition in the early universe, and then stretched to their current scale by 13.8 billion years of cosmic expansion. If that's right, these fields predate every star that has ever burned. They predate galaxies. They may be the oldest organized structures in the observable universe. The second explanation argues the fields were seeded by early quasars and massive stars, and then dispersed into the voids by galactic winds and jets over billions of years. Neither has achieved consensus. The Square Kilometer Array, a next-generation radio telescope currently under construction, has specific observing programs designed to eventually distinguish between them. In the meantime, something is maintaining an invisible magnetic architecture across the deepest emptiness in the known universe. Whatever organized those fields did, so either at the moment of creation or through a mechanism we haven't yet fully traced. Either way, the answer is extraordinary. Number 9. Rogue stars. In the 1990s, Hubble Space Telescope observations of galaxy clusters like Virgo and Coma began revealing a faint diffuse glow between the individual galaxies, not associated with any galaxy, not from any identifiable source, just there, spread across the intergalactic space between them. When astronomers analyzed that light carefully, they reached a conclusion that required some adjustment to process. The glow was starlight. There were stars out there, individual stars, billions of them drifting alone through the void between galaxies, unbound to any galaxy, orbiting nothing except the slow collective gravity of the cluster as a whole. The assumption had always been that stars are creatures of galaxies. They form inside galaxies, they live in galaxies, they die in galaxies. The idea of a star existing permanently in genuine intergalactic space, with the nearest other star potentially thousands of light years away, seemed like a footnote at most. It turned out to be one of the largest stellar populations in existence. In rich galaxy clusters, current estimates suggest that somewhere between 10 and 50% of all stars may exist outside any individual galaxy. The Virgo cluster alone is estimated to harbor hundreds of billions of these wanderers. James Webb Space Telescope observations beginning in 2022 confirmed the scale of the phenomenon with unprecedented clarity. These stars were almost certainly ejected during galaxy mergers. When two galaxies collide and interpenetrate, individual stars get flung outward at hundreds of kilometers per second, sailing beyond the edge of their home galaxy and into permanent exile. Every major galaxy merger in cosmic history scattered some of its stars into the void. There have been an enormous number of mergers, the math compounds. These stars almost certainly have planets. There's no reason they wouldn't. Those planets are drifting through regions of space where no galaxy is close enough to cast more than the faintest smear of light across the sky. Their night sky would be essentially pitch black, not the way a rural night sky is dark, actually dark. No galactic band stretching overhead, no visible neighboring stars, just faint distant galaxies hundreds of millions of light years away, and that's all. Whatever might exist on those worlds would have very compelling reasons to think the universe was nearly empty. They would be wrong, but they would never find out. Number 8. The temperature problem in the intergalactic medium. The gas filling the space between galaxies, a thin plasma called the intergalactic medium, should by all straightforward calculations be cold. There are no stars out there to heat it, no active nuclear reactions, no obvious energy sources of any kind. Simple models predict temperatures of tens of thousands of Kelvin at most, warmed gently by distant ultraviolet radiation from quasars slowly ionizing the surrounding hydrogen. When astronomers actually measured the intergalactic medium, they found something considerably more alarming. In many regions, it runs to hundreds of thousands of Kelvin, in some areas, millions. Temperatures that rival the outer layers of a star maintained across vast regions of near-perfect emptiness with no obvious fire nearby. This became known informally as the temperature problem. Something is pumping enormous quantities of heat into the void between galaxies, and for a long time the source was genuinely unclear. The leading explanation today involves two mechanisms working in concert. The first is helium ionization. Helium requires far more energetic radiation than hydrogen to be fully stripped of its electrons, and the objects capable of producing that radiation are quasars. A major burst of quasar activity between about 3 and 4 billion years after the Big Bang appears to have heated the intergalactic medium substantially during a period called helium reionization. A 2019 study using the cosmic origin spectrograph on Hubble provided strong supporting evidence for this. The second mechanism, proposed in 2012 by Broderick and colleagues, involves blazars, the most extreme class of active galactic nuclei. Their gamma-ray jets, pointing almost directly toward us, may be depositing heat into the surrounding intergalactic gas across millions of light years. Neither mechanism fully accounts for the temperature budget on its own. Together, they bring the models closer, but significant discrepancies remain, particularly in the densest filament regions where the temperature excess is most pronounced. The void between galaxies is not cold and quiet. It is hot in ways that required a decade of dedicated research to partially explain, and which still don't have a complete answer. Number 7. Fast radio bursts. On July 24, 2001, a flash of radio energy crossed several billion light years of intergalactic space and was captured by the Parkes Radio Telescope in New South Wales, Australia. Nobody noticed it had happened for 6 years. Astronomer Duncan Lorimer found the signal in 2007, sifting through archived data with his graduate student. When he analyzed the way the burst's different frequencies had spread out during their long journey through intervening electrons, the dispersion measure told an unambiguous story. This signal had come from well outside the Milky Way. In the span of a few milliseconds, whatever produced it had released more energy than the sun outputs over several days. Fast radio bursts, FRBs, were so extraordinary that significant portions of the astronomical community initially suspected they were some form of terrestrial interference, an equipment artifact pretending to be a cosmic signal. Years of additional detections and eventual real-time captures by multiple independent observatories settled that debate. They were real. They were extragalactic, and they were happening constantly, everywhere, in every direction. The Canadian Hydrogen Intensity Mapping Experiment, CHIME, a radio telescope in British Columbia that began operating in 2018, transformed the field almost immediately, detecting hundreds of FRBs and revealing a phenomenon far richer and stranger than anyone had anticipated. Some bursts repeat, some repeat with such unsettling regularity that there must be an underlying clock, some orbital or rotational period driving the cycles. FRB 180916 fires on a 16.35-day schedule with a precision that implies a physical mechanism, not a random process. In 2020, a breakthrough arrived from inside our own galaxy. An FRB was detected coming from SGR 1935 plus 2154, a magnetar about 30,000 light years away. For the first time, a source was directly identified. Magnetars, neutron stars with extraordinary magnetic fields, became the leading candidate for at least some FRBs. But magnetars cannot explain the full range of what's being detected. The precise repeating cycles, the range of energies, the variation in structure from burst to burst, the taxonomy of what produces these events remains genuinely open. By theoretical extrapolation, hundreds of thousands of fast radio bursts cross the observable universe every single day. We've cataloged a tiny fraction of them. They've been crossing the universe for billions of years longer than Earth has existed. We only began listening in the last few decades. Number 6. Supervoids and the cold spot. In 2004, while analyzing data from NASA's WMAP satellite, which had produced the most detailed map yet of the cosmic microwave background, astronomers noticed something wrong. In a patch of sky in the southern constellation Eridanus, the temperature of the ancient light from the Big Bang's afterglow was measurably, stubbornly lower than it should be. Not by a dramatic amount, by about 70 microkelvin. But the CMB fluctuations are only a few microkelvin across most of the sky, so a 70 microkelvin deficit in a coherent patch of that angular size was deeply anomalous. They called it the cold spot. 2 decades of analysis have not explained it satisfactorily. In 2015, a team led by Istvan Sapudi at the University of Hawaii identified a supervoid aligned with the cold spot's position on the sky, a region of space approximately 1.8 billion light-years across, containing roughly 20% fewer galaxies than you'd expect to find in a volume that size. It was the largest supervoid ever identified, and it offered a plausible mechanism. When photons travel through an expanding void, they can lose energy in a process called the integrated Sachs-Wolf effect, and that energy loss would show up as a cold patch in the CMB. The problem is the numbers don't fully add up. The supervoid accounts for some of the temperature deficit. It doesn't account for all of it. The cold spot is colder than the void alone can explain. The gap between what the void provides and what the data shows has generated increasingly exotic proposals. Among the more striking, some researchers have suggested the cold spot might be the imprint of a collision between our universe and an adjacent bubble universe during an inflationary period early in cosmic history. A bruise in the fabric of the CMB left by contact with something that exists outside our observable cosmos entirely. This is considered a fringe hypothesis by most cosmologists. It has not been formally ruled out. The Planck satellite's refined analyses confirmed the cold spot persists through even the most rigorous modern foreground removal. A billion light-year void, the oldest light in existence running measurably cold in one direction. Our best models falling short of a complete explanation, and one hypothesis that the answer might lie outside the universe entirely. If you're finding this channel for the first time, this is what we do here. Every week, we go somewhere the universe gets strange and follow it as far as the physics will take us. If that's what you want more of, now is a good time to hit subscribe and turn on notifications, because the next thing we cover, we post it, and you'll want to see it when it drops. We're only halfway through this list, and it gets significantly more unsettling from here. Number 5, dark matter and the scaffolding you can't see. In the 1970s, astronomer Vera Rubin and her colleague Kent Ford sat with rotation curve data from dozens of galaxies and found something that violated everything Newtonian gravity predicted. Stars at the outer edges of galaxies were orbiting just as fast as stars near the center, sometimes faster. According to the known distribution of visible mass, they should have been moving much more slowly. The galaxies should have been flinging their outer stars into space. They were not doing that, which meant something invisible was providing the gravitational glue. This was not a new idea. Swiss astronomer Fritz Zwicky had proposed in 1933 that galaxy clusters contained far more mass than their visible stars could account for. But Rubin and Ford turned that speculation into a measurable crisis. Galaxy after galaxy showed the same anomaly. The required mass simply wasn't there in any form that emitted or absorbed light. Dark matter is now estimated to make up approximately 27% of the total energy content of the universe. Ordinary matter, every atom in every star and planet and gas cloud ever observed, accounts for roughly 5%. In the intergalactic context, dark matter is the scaffolding of everything. It forms the invisible filaments along which the cosmic web is organized, the unseen halos that surround every galaxy and extend far beyond their visible boundaries, the gravitational backbone that determined where galaxies could form and where they could not. The most direct confirmation came in 2006 from observations of the Bullet Cluster, two galaxy clusters that had passed through each other at high speed. Gravitational lensing maps showed the mass, and therefore the dark matter, had separated cleanly from the hot gas during the collision, drifting ahead of it like a ghost moving through a wall. Despite 50 years of increasingly sensitive searches, dark matter has never been directly detected. The most sophisticated underground detectors ever built have found nothing matching the expected signal. The Large Hadron Collider at CERN has produced no confirmed dark matter particle. Every proposed candidate, WIMPs, axions, sterile neutrinos, primordial black holes, survives only because it hasn't been definitively ruled out. The architecture of the entire observable universe is built on a foundation of something we cannot see, cannot touch, and cannot detect with any instrument currently in existence. It outnumbers ordinary matter by more than 5 to 1. It determines the shape of everything. After half a century of searching, we don't know what it is. Number 4. Quasars. In 1960, astronomer Martin Schmidt was working at the Palomar Observatory in California, studying the optical counterpart of a radio source cataloged as 3C273. To every instrument, to every other astronomer who had looked at it, it appeared to be an unremarkable faint star. Schmidt took its spectrum and felt the ground shift beneath him. The spectral lines were red-shifted so dramatically that the object had to be approximately 2.4 billion light-years away. At that distance, for it to be as bright as it appeared through a ground-based telescope, it had to be producing more energy than an entire galaxy of hundreds of billions of stars, from a region of space no larger than our solar system. Quasi-stellar objects, quasars, turned out to be the most energetically extreme sustained phenomena in the observable universe. Supermassive black holes consuming surrounding material at such enormous rates that the infalling matter heats to millions of degrees and radiates across every wavelength simultaneously, outshining their host galaxies by factors of hundreds or thousands. Astronomers have now cataloged over 1 million of them. Most burned brightest in the distant past when the universe was younger and gas was more abundant. In February 2024, a team led by Christopher Wolfe published results in Nature Astronomy, confirming that a quasar designated J0529-4351 is the most luminous object ever measured. Its brightness exceeds the sun's by approximately 500 trillion times. The black hole at its center is consuming the equivalent of one entire solar mass every single day. The light currently reaching our telescopes left this object when the universe was roughly 1.5 billion years old. But quasars don't merely shine in isolation. They reshape the cosmos around them. The jets they launch, beams of magnetized plasma accelerated to nearly the speed of light, can extend for millions of light years into the surrounding intergalactic medium, injecting energy equivalent to trillions of supernovae into gas that would otherwise collapse and form new galaxies. This process, called quasar feedback, is now understood as one of the primary mechanisms by which the universe regulates star formation across cosmic time. The violence inside those cores is not a local event. Its effects echo across the entire intergalactic environment. Martin Schmidt found a dim point of light that turned out to be an engine powerful enough to reshape the structure of the universe. We still don't have a complete physical explanation for how a black hole generates and sustains jets millions of light years long. Number 3. The Hercules Corona Borealis Great Wall. In 2013, a team of astronomers was mapping the distribution of gamma-ray bursts across the sky using these extraordinarily powerful explosions as tracers of where matter concentrates across the distant universe. Gamma ray bursts are detectable across billions of light years and mark the locations of massive stellar collapses and neutron star mergers, making them useful probes of large scale structure in a universe otherwise too vast to map directly. What the team found in a region of sky spanning the constellations Hercules and Corona Borealis, published in Astronomy and Astrophysics in 2014, was a statistical clustering of gamma ray bursts so pronounced and so vast that it directly challenged one of the most load bearing assumptions in all of modern cosmology. That assumption is the cosmological principle. The idea that at sufficiently large scales the universe is homogeneous and isotropic, the same in all directions, the same at all locations, no preferred axis, no special regions, no coherent structure above a certain scale. It isn't merely a working assumption, it is the foundation on which virtually every equation describing cosmic expansion, structure formation, and dark energy behavior rests. Without it, cosmological modeling becomes dramatically more complex, possibly intractable. The cosmological principle sets a theoretical ceiling on how large any coherent structure can be, approximately 1.2 billion light years. Beyond that threshold, the universe simply should not show organized clustering. The Hercules Corona Borealis Great Wall is estimated to span approximately 10 billion light years. For a structure of that scale to exist through gravitational assembly, the universe would have needed far more time than it has had. The cosmos is 13.8 billion years old. Standard physics says there has not been enough time for gravity to arrange anything 10 billion light years across into a coherent pattern. The finding remains actively debated. The structure is identified through statistical excess of gamma ray bursts, not through direct imaging. Some cosmologists argue it may reflect observational bias or insufficient sample size. Others have pursued independent confirmation with mixed results. It has not been formally accepted as a definitive physical structure. It has not been dismissed. It persists in the literature as a serious, unresolved anomaly. If it is real, it does not merely challenge the cosmological principle, it shatters it. And a universe that breaks its own foundational organizing rule at sufficient scale is a universe whose governing equations may need to be rebuilt from first principles. The most unsettling possibility is not that we found something very large, it is that we found something that should not exist at all, and we cannot yet say with certainty whether it does or doesn't. Number 2. The axis of evil. In 2003, the WMAP satellite delivered what was supposed to be the most precise map ever made of the cosmic microwave background, the ancient light from 380,000 years after the Big Bang. A snapshot of the infant universe, the seeds of everything that followed, encoded in temperature fluctuations of a few millionths of a degree, scattered across the full sky. Cosmologists expected the map to be consistent with isotropy, a universe with no preferred direction, no special axis, fluctuations distributed randomly as physics required. In 2005, Kate Land and João Magejo of Imperial College London published a paper in Physical Review Letters announcing what they called, with deliberate provocation, the axis of evil. The largest scale features of the CMB map, the quadrupole and octupole moments, the broadest temperature patterns visible across the entire sky, were not randomly distributed. They were aligned with each other, and aligned with the plane of Earth's orbit around the Sun. The cosmological principle demands the universe look the same from everywhere. There is no physical mechanism under any standard model that would make the largest features of the primordial universe appear to know where our planet's orbital plane is. The probability of this alignment occurring by chance was calculated at less than 1%. It was, and remains, deeply strange. This was not a measurement artifact. The Planck satellite, a more sophisticated instrument operated by the European Space Agency, released its own CMB maps in 2013, 2015, and 2018, each time with improved sensitivity and more rigorous foreground removal. Each time, the axis of evil was still there. Every plausible systematic error has been investigated and found insufficient. The alignment has survived more than 2 decades of scrutiny. Proposed explanations span a wide range. Some researchers suspect residual contamination from local structures in our galaxy or solar system that hasn't been fully subtracted. Others have proposed the universe may have a non trivial topology, a finite geometry, perhaps a torus or something more exotic that would impose a preferred direction onto the CMB. A minority of theorists have suggested it as evidence for cosmological models that are fundamentally anisotropic at the deepest level. None of these explanations has achieved consensus. What has been written into the oldest light in the observable universe, at the very largest scales we can measure, appears to know where we are. That is not supposed to be possible, that it persists, confirmed and reconfirmed across 2 generations of satellite observations, unchanged by every attempt to explain it away, means that whatever lies between and beyond the galaxies may be organized in ways our current physics cannot yet describe. Number 1. Dark energy. In 1998, 2 independent teams of astronomers set out to measure how quickly the expansion of the universe was slowing down. The expectation was unambiguous. The Big Bang had sent everything flying outward. Gravity, the universal attraction of every mass for every other mass, was breaking that expansion. The only real question was whether the universe would eventually reverse into a big crunch, or whether it would expand forever at a steadily decreasing rate. Both teams used Type 1a supernovae as their measuring tool. These explosions have a consistent intrinsic brightness that makes their apparent faintness in our sky a reliable indicator of their distance. Saul Perlmutter's Supernova Cosmology Project and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, gathered their data separately, analyzed it separately, and arrived at the same answer. The expansion was not slowing down, it was accelerating. Something was pushing the universe apart with increasing force, winning against gravity across every scale large enough to matter, and growing stronger over time. Perlmutter, Schmidt, and Rees received the Nobel Prize in Physics in 2011. The thing they discovered was named dark energy, and it has resisted every attempt at understanding ever since. Dark energy constitutes approximately 68% of the total energy content of the universe. Ordinary matter, every atom in everything you have ever seen or touched or thought about, accounts for roughly 5%. Dark matter accounts for 27%. The remaining 68%, the majority of everything that drives the behavior of the cosmos, is a substance or property we cannot detect, cannot produce, cannot interact with, and cannot explain. It doesn't clump, it doesn't form structures. It appears perfectly smooth and uniform, filling all of space at constant density, exerting the same repulsive effect everywhere, growing more dominant as the universe expands. The leading theoretical candidate is vacuum energy, the energy of empty space itself, represented in Einstein's equations by the cosmological constant he introduced and then called his greatest mistake. When physicists calculate what the energy density of the vacuum should be from first principles using quantum field theory, they get a number. When they compare that number to the observed value of dark energy, the discrepancy is 10 to the power of 120. That is a 1 followed by 120 zeros. It is described without any hyperbole as the single worst prediction in the history of physics. Our deepest theory of matter and energy and our best theory of gravity do not merely disagree on dark energy. They disagree by the largest margin ever recorded between a theoretical prediction and an observational measurement. Dark energy's effects are exclusively intergalactic. Within galaxies and within galaxy clusters, gravity still dominates, structures hold together, but in the vast spaces between those clusters, dark energy is winning, pushing the universe apart faster than it was yesterday, faster than it was a billion years ago, slower than it will be a billion years from now. Galaxies outside our local group are already accelerating away from us. Given enough time, they will cross our cosmic event horizon and vanish, unreachable, unobservable, forever. 2 trillion years from now, if anything still exists to look, every galaxy outside whatever remains of the local group will have disappeared behind that boundary. The night sky will be essentially empty. A civilization born into that future universe would have no way of knowing that 2 trillion years earlier, the sky blazed with galaxies in every direction. They would have no evidence the Big Bang occurred, no evidence the universe had ever been anything other than cold and dark and quiet. We happen to exist at the one brief window in cosmic time when the evidence is still visible, when the expansion is still young enough that distant galaxies haven't yet crossed the horizon, when the CMB still carries the fingerprints of the first light, when the web of filaments and the rogue stars and the magnetic fields in the void are all still detectable, all still there, all still waiting for us to understand them. The space between galaxies is not nothing. It is where most of the universe lives. It is where most of the mass hides. It is where the oldest organized fields in existence are threading through near perfect emptiness. It is where energy we cannot explain is systematically disassembling everything gravity ever built. The emptiness between the galaxies is the most important place in the observable universe. And we have barely begun to read it.